Last time we talked about artificial gravity as the fix most likely to actually happen. So let's answer the obvious next question. How does it actually work? Start with how science fiction usually shows it, because almost none of it is real physics. It's a convenient shortcut. Walk around the Enterprise in Star Trek, and gravity just works everywhere, all the time, with no visible mechanism at all. The official in-universe explanation, when the shows bother to give one, involves gravity plating, lining the decks, powered by graviton generators. Even scientists who consult on the franchise are upfront about what that actually is. A hand-wavy placeholder. Gravitons, hypothetical particles that would carry the force of gravity, have never been detected, and even if they exist, nothing in real physics suggests you could stuff a device under a floor panel and have it radiate a controllable gravitational field on demand. It's technobabble, not technology. Stargate does the same thing, just without even that much explanation. Step onto a ship built by the ancients or the Goa'uld, and full gravity is simply already there. No rotation, no visible generator, no discussion required. It's treated as a given, the same way the ship simply has air to breathe. Here's the actual problem with both versions. General relativity ties gravity directly to mass and energy. A gravitational field isn't a separate thing you can generate and beam somewhere. It's what mass is, warping the space around it. To create Earth-strength gravity in a room the size of a starship bridge without spinning anything, you'd need to somehow concentrate an enormous amount of mass energy in a way nothing in known physics allows. It's not that we haven't invented the device yet, it's that the concept, as science fiction depicts it, doesn't correspond to anything physics currently thinks is possible. Deckplate gravity is a production choice, not a prediction. It's dramatically far cheaper to film actors walking normally than to rig them on wires for every single scene. So if beaming gravity directly onto a floor isn't real, what actually is? This is where the good news comes in. The short version, you spin something. The longer version is a 100-year-old idea that's genuinely harder to build than it sounds, and the reason why is more interesting than the concept itself. Start with the physics because it's simpler than you'd expect. There's no such thing as a machine that generates gravity directly. Nothing produces a gravitational field on demand. What you can do instead is fake the feeling of gravity using rotation. Spin a structure, and anyone standing inside it, on the inner surface of the outer wall, gets pushed outward, the same sensation as being pressed into your seat on a fairground ride. Your body can't tell the difference between that outward push and the pull of real gravity. That's it. That's the entire trick. And unlike gravity plating, it's been demonstrated for real. This idea is over a century old. Konstantin Tsiolkovsky, the Russian rocket pioneer, described the concept as early as 1903. Hermann Potocznik sketched an actual rotating, wheel-shaped station in 1929. Werner von Braun picked it up in 1952, proposing a station generating a third of Earth's gravity from a wheel about 38 meters across, spinning under 3 times a minute, and it became genuinely famous in 1968 when 2001, A Space Odyssey put a rotating station on screen and gave millions of people their first real mental image of how this was supposed to work. The idea has been sitting there, fully worked out on paper, since before anyone had even reached orbit, so why don't we have one? Because the first time humans actually tried it, in 1966, it barely worked at all. Gemini 11 astronauts Pete Conrad and Dick Gordon tethered their capsule to a spent Agena rocket stage with a 30-meter nylon line, then fired thrusters to set the pair slowly rotating around each other. The first artificial gravity ever generated with humans present. The result, about 0.005 g. A fraction of Earth gravity, detectable only because a loose camera drifted gently toward the back of the cabin. Conrad and Gordon didn't feel a thing. It proved the physics worked. It also proved just how much rotation, or how much radius, you actually need before artificial gravity becomes something a human body can feel at all. That's the real engineering problem. and it comes down to two dials you can turn against each other: radius and speed. Rotate a structure fast enough, or make it wide enough, and you get stronger artificial gravity. The maths is exact. Acceleration equals the rotation speed squared times the radius. The problem is that rotating too fast, especially with a small radius, triggers something called the Coriolis effect. Turn your head inside a fast-spinning structure, and your inner ear reports twisting, tumbling sensations with no matching visual cue. It's severely disorienting and reliably causes nausea. NASA's own guidance puts comfortable rotation at somewhere under 4 to 6 rotations per minute for most people without training. To get a full Earth gravity at 4 RPM, you need a structure with a radius of about 56 meters, meaning the station itself would need to be well over 100 meters across. That's not a space station. That's most of a football stadium spinning in orbit. So there are really only two honest paths forward, and they trade off against each other directly. Build big and spin slow, the Von Braun wheel, the 2001 station, vast roadmap for a future rotating outpost, planned to spin end over end at 3.5 RPM. Comfortable, close to how gravity actually feels, but expensive and genuinely enormous to launch and assemble. Or build small and spin fast, a compact onboard centrifuge, more like a piece of gym equipment than a living space that astronauts step into for exercise sessions rather than living in permanently. This needs much faster rotation, upwards of 15 RPM, which is far more disorienting, but recent research is more encouraging than you would expect here. Subjects can meaningfully adapt to that kind of spin rate through a structured, roughly 50-day training program, gradually increasing exposure until the disorientation fades. It's not comfortable on day 1, it's workable by day 50. Where this actually stands right now, honestly, is closer to planned than built. VAST, the private company building Haven 1, due to launch in 2026 as the first commercial space station, has explicitly put full artificial gravity on its roadmap, not for Haven 1 itself, but for a later station beyond it, spinning end over end at 3.5 RPM. That's a real, funded, named engineering target from a company already building hardware, not a concept sketch. It's the most concrete, this is actually happening, version of a 100-year-old idea currently on the table. So how do we generate artificial gravity in space? We already know exactly how. The physics has been settled since 1903, and it's simpler than most of the propulsion problems we've covered on this channel. What's taken over a century isn't figuring out the idea. It's finding a way to build something big enough to spin comfortably, or training bodies to tolerate something small enough to actually launch. Both paths are finally, genuinely, on someone's engineering roadmap. We're not waiting on a discovery anymore. We're waiting on a construction schedule. If you found this useful, hit subscribe for more of these, and a like genuinely helps the channel more than you'd think.